So you're still thinking of me, just like I know you should. I cannot give you everything, you know I wish I could. I'm so high at the moment, I'm so caught up in this. Yeah,
Hi everybody, here is our video on implicit differentiation where you're going to learn how to do a derivative of a different kind of equation, which usually will not be a function anymore. The thing to keep in mind is we're still doing rates of change here, so we're still in our big derivative unit. We're still going to be doing lots of derivatives, but the functions we're taking the derivative of are not going to be clear. So everything that we've done the derivative of so far has been y equals something, and then you just did the derivative of this and you replaced y with dy dx, and over here was the derivative. Now we're going to be doing equations where you're going to be finding the derivative of a hidden function, meaning it's not just going to be y equals. You'll have equations where y is mixed in on each side of the equation, and I'll show you a bunch of examples of that. So before we start, let's talk about what the word implicit really means here. Again, as of now, you've been doing equations where it was just y equals something in terms of x. So that is an explicit function here. It's just y equals, and then there's a bunch of x stuff on the other side. You only had one y, and that one y was alone. So these are all examples of things that you have done derivatives of so far. And I'm actually going to do the derivative of each quick just to focus on the notation because that's going to be important whenever we do the implicit differentiation. Usually whenever you did a derivative, you replaced y with y prime. But remember, we can also do the Leibniz notation and replace y. And whenever we do the derivative of y, replace it with dy dx, which means the derivative of y with respect to x. And then you would just put 3x squared, for example. Here, y, you would replace it with dy dx when I do the derivative and cosine x. Over here, again, dy dx. And then you would do your quotient real quick. Ho d hi minus hi d ho all over ho ho. And obviously you would simplify that, but we're not going to do that right now. The whole point is anytime you did a derivative of y with respect to x, you put dy dx. That's going to be the whole premise of this video here. So just keep that in mind the whole time we're doing this here. Again, dy dx, derivative of y with respect to x. So let's look at some functions that are not defined explicitly. They are going to be defined implicitly. So this is what these are going to look like. You'll have an equation and there's not just one y. There can be several y's, and it's not just y equals. Y is in the mix of things here. It's not explicitly stated. So usually you will not be able to solve for y easily. I'll do one where you can solve for y easily, but usually y will be so mixed in that you can't even get it alone. So the question is, how am I going to do a derivative of it if y is not even alone? So you're going to need implicit differentiation, and that's what's going to let you do dy dx. Now, because these are not functions, now let's review why this is not a function here. We have this thing called the vertical line test, remember? And this one here is the equation of my first equation. So make sure you're writing all these notes down here. Pause the video now or at the end whenever you want to write all this down. So Desmos has this really cool implicit grapher that you can type in implicit functions and it'll graph them for you. And they're not functions. Now your graphing calculator would not graph these because your graphing calculator only wants to graph a function. But Desmos can do non-functions. And notice for every single x, like if I was at 1.1, there's 2 y's. All these x values, there is 2 y values. The only x value that only has 1 y value is way over here where it only touches once. But for pretty much every x, there's more than 1 y, and that's going to make tangent lines different for us here. So if we want the slope of a tangent line or the derivative, let's look at 1 here. I'm going to focus at 1 for most of this video. If I wanted the derivative at 1, you're going to need more information than just 1, because if you look at 1 carefully, there's a point here, oops, and there's a point here. So if you said, hey, find the tangent line at 1, notice at 1 there's a y value here at 1, and then there's a y value here, which looks like negative 1 point something. So you don't know if it's this tangent line, which has a positive slope, or this tangent line, which has a negative slope or negative derivatives. So before, all you had to do was plug x into a derivative to get a slope, but here you can't just plug x in because there's more than one case. So you're going to have to use the x and the y. And down here, again, I'm just noting that we failed the vertical line test. Now, implicit differentiation works because we're not going to go too far into this, but just realize that even though the whole graph as a whole is not a function, you can break it into things called branches. So for example, if I cut this function here, wait, let me fix that. I could break the function up here into an upper branch, which is this. That's supposed to be right on it. And then I can cut it into a lower branch, which is down here. And by breaking it up into branches, each of those branches individually is a function and passes the vertical line test. It's just when you combine it as a whole, it'll fail the vertical line test. So that is how we can still do implicit differentiation, because in those individual branches, those are each functions. So pause the video if you need, if you haven't gotten all that written down. Okay, so you're gonna have to remember two notation things here when we do this, d dx versus dy dx. So d dx, if someone puts that down, that is actually a command to you, and it's saying, hey, take the derivative of this equation with respect to x. The reason it's with respect to x is because it's d dx. That means in calculus language, derivative with respect to x. So x is your variable, and if you see d dx, that means you haven't done a derivative yet, but you should do a derivative. Once you see dy dx, that means the derivative is already done. So you already did the derivative. So once you're putting dy dx, you're telling someone, hey, I already did the derivative of y with respect to x. So they look very similar, but there's a big difference between the two. Now, before we get to the more complicated equations, I'm going to do a couple basic ones just so you get the hang of how this whole implicit differentiation actually works. And they're going to be very basic, but you're just starting, so we have to start somewhere. So let's do the derivative with respect to x of y to the fourth. So again, d dx says, hey, I want you to do the derivative of y to the fourth. So remember, before, if I had y and I wanted the derivative of y, we would put dy dx. And the real reason we put dy dx when I want the derivative with respect to x is the derivative of y, so d dx of y, the derivative of y is actually 1, just like the derivative of x is just 1. So y's derivative is 1, but because these variables didn't match up, I had to multiply 1 by dy dx, which means derivative of y with respect to x. And 1 times dy dx is dy dx. So here, I'm going to do the derivative of y to the fourth, which using the shortcut is 4y cubed. But because these variables are not the same, I have to multiply by dy dx. Now you might be wondering, we never did that before, that's kind of weird. But we actually did, we just didn't really think about it. Because let's think about what we used to do. D dx of x to the fourth. Derivative with respect to x of x to the fourth. You would just say, hey, that's 4x cubed, and move on. But behind the scenes, what was really happening is you multiply 4x cubed by derivative of x with respect to x. And dx is just 1. So that's why you could just walk away with 4x cubed. So really, you were always multiplying by something like this. It's just sometimes it cancels, and you don't have to worry about it. Similarly, what if I had the derivative with respect to y of y to the fourth? So we're going to start doing the derivative of things not always with respect to x, especially when we get to something called related rates. So you have to get used to different variables here. If I'm doing the derivative with respect to y, so I'm going to do the derivative of y to the fourth, which is 4y cubed. Then I'm going to multiply by dy, because I did derivative of y, over dy, because I did the derivative with respect to y. dy cancel, so I just have 4y cubed. Let's do one more really quick. What if I had d dx of 3y to the 8th? So the derivative with respect to x. So I'm going to do the derivative of just 3y to the 8th, 24y squared, but then I have to multiply by derivative of y with respect to x, because my variables, again, don't match. Basically, anytime the variables don't match, you have to put this implicit differentiation statement afterwards. Okay, so let's do a semi-easy example here. And we're going to do a circle. So x squared plus y squared equals 4. And I graphed that on Desmos here. And notice I can have tangent lines at any x. They would just graze the curve at one point. These are bad tangent lines, but pretend they're good tangent lines. So notice as a whole, this circle is not a function, but this is an example of a implicit function where I could solve for y. So I could just subtract x squared from each side and get y squared equals 4 minus x squared. If I do a square root, I get this statement. So I have y equals positive root and y equals negative root. So the positive root would be the upper branch and the negative root would be the lower branch. So again, this is the whole idea of breaking an implicit non-function into branches so that they are functions. So let's go ahead and do a derivative here. So x squared plus y squared equals 4. So I'm going to do the derivative with respect to x. So my goal is to get dy dx. All right, so I'm going to do the derivative of 2x, and since it's with respect to x, I just have to do 2x. Now I'm going to do the derivative of y squared, which is 2y, but again, because y and x don't match, I have to multiply by dy dx. Derivative of a constant is 0, no matter what. So I need to get dy dx alone, and I'm going to subtract 2x from each side, so I'm moving this to the other side. Then I can divide by 2y. That cancels. So I have dy dx equals, and I'm going to cancel the 2's, and I get negative x over y. So negative x over y represents the derivative at any xy ordered pair. So if you wanted an actual tangent line at a point, all you'd have to do is plug in an actual ordered pair, and you would get the instantaneous rate of change, or derivative, or slope of the tangent line. All the same thing. Let's do one where, well, to get to more complicated ones, we're going to have to talk about what would happen if I had x times y or x divided by y. So as soon as you've seen multiplication, you need to be thinking product rule, which is this right here. And it's still the normal product rule. It's just that we have to think about implicit differentiation. So we're doing the derivative with respect to x. So the derivative of x, so I'm going to do f g prime plus f prime g. And again, Ryan Rossi, the order does not matter here. I'm just going to do regular f first. So I'm going to put the x down. Then I multiply by g prime. So the derivative of y is 1 times derivative of y with respect to x, dy dx. Then I'm going to add, and I'm going to multiply by f prime. So the derivative of x is just 1. Don't have to put dy dx after because x and x match. And then just put g, so y. Okay, here I'm going to do quotient rule because I'm dividing x and y. So here's a quotient rule that you know. So I'm going to do the bottom, which is y. Then I'll multiply by the derivative of the top, which is 1, minus top times the derivative of the bottom, which is dy dx, all over bottom squared, like so. So now that we have the basics of implicit diff and we talked about how product and quotient rule play in, we can get to more complicated examples, which I'll do in the next video.